All right, let's get right into it. We're about to pull back the curtain on a piece of technology that's, and I'm not kidding, absolutely everywhere. It's this invisible force running pretty much every part of your life, but most people have never even heard its name.
I mean, really think about that for a second. You've got this one outlet in your wall, and it's pushing out this powerful, constant stream of electricity. So how on earth does your delicate little smartphone not just get completely fried? And how does a massive TV get the exact juice it needs to work perfectly?
Well, it's not magic, even though it kind of feels like it. The answer is this incredible field of engineering called power electronics. You can think of it as the invisible brain that's intelligently managing all that electricity, sitting right between the power outlet and all your devices.
So here's what we're going to break down. We'll start with this unseen power controller, what it is and where it is. Then we'll define power electronics itself. We'll get into the real secret sauce, the magic of switching. We'll see it in action controlling an electric motor, look at how it shapes all modern power, and finally, tie it all together to see what this means for our electric future. And look, when I say this stuff is everywhere, I really mean it. This isn't some far-off, futuristic idea. It is the fundamental, core technology that makes our modern world modern.
It's in the massive systems that connect solar and wind farms to the grid. It's what makes the electric car in your garage go. It runs the giant motors in our factories. And yeah, it's right down to that tiny little charger for your phone or your laptop. Every single one of them depends on power electronics to even work.
So what is it, really? Let's peel back the layers and look at the official definition and the main parts to get a super clear picture of what we're talking about. Okay, there are two words here that are absolutely key: control and conversion. See, power electronics isn't about making power. It's about taking the power we already have and precisely shaping it, managing it, and converting it into the exact form that's needed for any specific job. And pretty much every system looks like this. You've got your power source, say the outlet in the wall. You've got the load. That's the thing you actually want to power, like a motor or a light bulb. And then, sandwiched right in the middle, you have the two most important pieces: the power converter, which you can think of as the muscle, and the controller, which is the brain telling the muscle exactly what to do.
And yeah, the source material really hits the nail on the head here. The converter is the absolute heart of the whole system. It's where all the magic happens. It takes that raw, brute force electricity from the source and completely transforms it.
But how does it do this so incredibly well, so efficiently? Well, the secret is something that's both mind-blowingly simple and totally clever. It all comes down to the switch.
Okay, picture this. The old way to control power was kind of like trying to control water flow by just leaving a faucet halfway open all the time. Sure, it works, but it's super wasteful. You're fighting the flow, and that wastes a ton of energy as heat. The new way, the power electronics way, is like turning that faucet on and off full blast thousands of times a second. But just changing how long it's on versus off, you can get any average flow you want with almost zero waste.
And the physics behind this is just so cool. Think about it. When a switch is fully off, no electricity can flow, right? So the power loss is zero. And when it's fully on, it's like a perfect piece of wire with no resistance. So again, the power loss is practically zero. By only ever being in one of these two no-waste states, these systems can hit efficiencies of over 95%. That is just incredible.
All right, so we've got this amazing idea of super fast, super efficient switching. That's the theory. Now let's see how it's put into practice to do something really common, like precisely controlling the speed of an electric motor.
And this is the million-dollar question, isn't it? It just feels wrong. How can a simple digital on or off action create that perfectly smooth analog control you need for something like a motor's speed?
The answer is actually really beautiful and elegant. The way it works is the controller creates this very fast, repeating triangular wave, just a constant up and down signal. Then it compares your desired speed, which is a control signal, to that triangle wave. Anytime your signal is higher than the triangle wave, the switch flicks on. The second it's lower, the switch flicks off.
And that simple comparison has a direct result. If you turn up your control signal, meaning you want to go faster, it's going to be higher than that triangle wave for a longer slice of time. That makes the on pulses wider. And those wider pulses increase the average voltage the motor sees. So to the motor, it doesn't feel like it's being turned on and off. It just feels a smooth increase in power, and it speeds up perfectly. It's pure digital control creating a perfect analog result. Amazing.
Now, this whole idea of controlled switching, it's not just for making motors spin at the right speed. It's the key that unlocks our ability to change electricity from any form into any other form we could possibly need.
So, for instance, a rectifier takes the AC power from your wall and turns it into the DC your phone battery needs. That's what's in your charger. An inverter does the exact opposite. It takes DC from a solar panel or a battery and turns it into AC for your house or the grid. All these different converters are just the basic building blocks that let all of our different electrical gadgets and systems actually talk to each other.
And look at this. Don't worry about all the crazy lines on the graph. Just appreciate the big picture. This shows the insane level of control we're talking about. This is power electronics perfectly manipulating voltage and frequency to control a massive industrial AC motor. We can squeeze every last bit of performance and efficiency out of it, at any speed. That's power.
Okay, so let's pull it all together. We've gone through the what and the how. Now for the most important question, why? Why does this invisible technology matter so much for all of us and for our future?
If you remember just 3 things from all this, make it these. First, power electronics is all about intelligent control. Second, the secret ingredient, the magic, is that incredibly fast and efficient power switch. And third, and this is the big one, this control is the single enabling technology that makes things like renewable energy, electric cars, and all of modern industry even possible. It's the linchpin holding it all together.
The simple fact is, without power electronics, our modern world just stops working. And as we push for more efficiency, a cleaner grid, and smarter devices, its role is only going to get bigger and more important. Which really just leaves us with one final exciting thought. What new breakthroughs? And what kind of future will this invisible controller power up next?